Right, we're so good. Okay. And we are here. We are here. Right, so we are beginning our discussion right now, focusing on aspects that relate to electricity. And we are looking first at question 8. The battery in the circuit shown below has an EMF electromotive force of 12 volts and an unknown internal resistance there. So there's an internal resistance small r. The resistance of the connecting wires and the ammeter is negligible. Okay, good. We continue with looking at further questions. Right, we're told that switch S is open. Write down the reading on voltmeter V1. Switch S is open, we can see there. The switch is open. So we need to write down the reading on voltmeter V1. Okay. Right, so and to do that is pretty very straightforward, and we analyze what that means. Okay, if the switch S is open, how do we then answer this question? But how do we know the reading on voltmeter V1? V1 measures the voltmeter reading across the battery, and now the question becomes, what is the reading there? Okay, so obviously it will read the following, right? The EMF is that one there, so it will actually read 12 volts. So the reading is exactly 12 volts, which is the reading on V1. And then now we are saying, what is the reading on V2, voltmeter 2? The switch S is open, so this is the positive terminal of the cell, and that is the negative. So the current flows from the positive terminal through the circuit, and obviously there will be no current flow because of the switch S that is open. So in other words, no reading there because there's no current flowing because the switch is open. So which means that voltmeter 2 will have a reading of 0 volts. Okay, right. Switch S is now closed. And if switch S is now closed, so they decide to have it closed. Okay, there. The reading on the ammeter is 1,2 amperes. Okay, so the reading on the ammeter is 1,2 amperes, 1,2 amps. Okay, you can put a comma there. And the power dissipated in resistor R is, okay, there's resistor R and there's a power rating they've given there. The power rating is 5,76 watts. Okay. Define the term power. What does power mean? What is power? Okay, power is defined as the rate at which work is done. Okay, the rate at which work is done, or energy is transferred, the rate at which work is done, or the rate at which energy is transferred. Okay. Or if they don't use the word transfer, the rate at which energy is expanded. Okay, so we can use that definition of power, the rate at which work is done, or the rate at which energy is transferred or expanded. Some calculations: calculate the resistance of resistor X. And where is resistor X? Here it is. We now want to find the reading on that resistor. What is the reading? Okay. It's easy to find the reading on that resistor because we already know the power, and we know that power is I squared R. That's one formula for power. Okay, so we already know therefore that the power is 5,76 watts, which equals the I, which is 1,2 squared, and the resistance is R, and this means that R is 5,76. You divide that by 1,2 all squared, and what is the resistance? I use the calculator there. It becomes exactly 4 ohms. So we have that the resistance is 4 ohms. We used the formula for power because they'd given us the power. There, so power is I squared R, where I is the current and R is the resistance. Okay, so the couple of formulas we learn, but this is not the only formula for power. We also know that power is also VI, potential difference by the current. But we also know that power is the potential difference squared over the resistance. So we can use any of these to do the calculations. For example, another student can come and use this particular one here. Okay, we can use P equals power equals VI, and then say the power is 5,76, which equals the potential difference into 1,2 of the current. And then at this point, you can be able to get the potential difference. So which means the potential difference, you divide 5,76 by 1,2, and then you get 4,8 volts. After you found the volts, the potential difference, you use Ohm's law, V equals IR. This is Ohm's law. And then after you used this one, you already know that V is 4,8, which equals 1,2 of the current, and then you multiply by the resistance, which means the resistance is 4,8 divided by 1,2, and the answer becomes exactly 4 ohms, and that sounds all right. So that kind of thing. All right. All right. So in 8.4, the total external resistance of the circuit. The total external resistance of the circuit. So the total external resistance of the circuit, it is the external resistance, not the internal. So at this point, now the switch, so now you need to combine all this and be able to see that this and that are in series. All right, so the series ones, you add them up. So this whole circuit diagram is going to reduce to the following. So it's going to reduce to this, and then this. Okay, so you can draw it like that, doesn't matter. And then you say this is 6 ohms, and then this is 2,4 plus 6, which is 8,4 ohms. Right, so giving us a parallel combination. Okay, this one obviously becomes in parallel with those two put together. And then now we have just these parallel resistors to deal with. So if they say you need to find the total external resistance, so in 8.4, we're going to do the following. So in 8.4, then you're going to say 1 over R parallel is 1 over R1 plus 1 over R2, which means that 1 over R parallel is 1 over 6 plus 1 over 8,4. And then now this is what we get. So R parallel, if you add all this, would be the same as 3,5 ohms. Okay, if you have parallel resistors, you can also say use a direct formula. The direct formula is that if they are parallel, so you can say R1 resistor 1, resistor 2, and then you say divided by resistor 1 plus the resistor 2. So this formula works for the parallel combinations, so that you have, there's a resistance of 6, and then a resistor of 6 ohms, and this one is 8,4 divided by 6 plus 8,4. Goodness me, what answer do you get here? You get 3,5 ohms. Okay, so the two answers are the same depending on the approach. It's actually very much independent on the on the approach you use. Okay, so what is R total? Which means that now the total resistance R total is the parallel combination plus the so you dealt with the parallel combination plus this one you got, but obviously we saw that this resistor is actually 4 ohms, so which means therefore you shall have this one plus 4 ohms, and therefore you deal with this one, you add them up, so it is 3,5 ohms plus 4, which is exactly 7,5 ohms, 7,5 ohms. Okay, so that's the answer we get there. Right. In which case, then we continue. We continue. That is the total external resistance of the circuit we've got, which is 7,5 ohms. The reading on voltmeter V2, let's find that one in 8.5. The reading on voltmeter V2. So obviously you can see that voltmeter V2 focuses on the parallel combination. So the parallel combination of these two are in series, and therefore in parallel with this. So you have that it focuses on the parallel combination. So the reading on voltmeter V2 is going to be V parallel, which is equal to, according to Ohm's law, V is equal to IR. So what is I here? So I is actually obviously the actual reading on the ammeter, which is 1,2 amperes. So you write here 1,2 amperes into the resistance. So the resistance here of the parallel combination, we've already seen the resistance of the parallel combination is actually 3,5 of the parallel combination. So if you put them together, we get 3,5 ohms, and then use the calculator to multiply 1,2 and 3,5, we get exactly 4,2 volts, and that gives us the reading on voltmeter V2, which is the reading across the parallel combination of the resistors there in the circuit diagram. Okay, so obviously this becomes exactly 4,2 volts. A length of wire of negligible resistance is used to connect P to point Q in the circuit. The length of wire of negligible resistance is used to connect point P to point Q in the circuit. Okay, let's see point P. There's the wire that has been used. Okay, so is used to connect point P. Here is this one and point Q. All right. It has negligible resistance. How will the reading on voltmeter V1 be affected? Choose increases, decreases, or no effect. Explain your answer. So let's look at 8.6. Right, so at this point, because this wire is actually of negligible resistance, how will the reading on V1 be affected? So V1 measures the potential difference across the battery. How will the reading there be affected? Okay, so there it is. All right, so let's see what we can say here. Let's see what we can say. Right, so in other words, we take this wire and we connect. This wire has negligible resistance, and we put it there like that. Right, so let's see what the reading is going to be. Right, if we do that and we just put that wire there, the reading on voltmeter V1 in 8.6, obviously it decreases. The reading decreases, and we're going to state the reasons why that is the case. So the reason is that in 8.6, total resistance decreases. Okay, so when the total resistance decreases, somebody can say, we know that the total resistance decreases because that wire has negligible resistance. And then obviously the observation is that therefore, because the resistance decreases, therefore the current increases. Okay, because it's inverse proportion sort of using R equals V over I Ohm's law, where we say the total resistance decreases, we expect an inverse relation. When the resistance goes down, we expect the current to go up there, and therefore that is the observation. But we can make other assertions about the internal voltage increases. So we can also make the comment that V internal, right, V internal, or something we call the internal voltage, something we call the lost volts. The lost volts increases. Or another person can make an observation of the what I call the external. I've already looked at the internal, so you can make an assertion about the external. So V external. In other words, external voltage decreases. External voltage decreases. Right, so those are the reasons why if you put the wire there, as I explained above, you'll have that the reading on the voltmeter V1 will then decrease, okay, because the total resistance decreases, which leads to an increase in the current. Okay, right. And so now that is what we need to observe. Okay, you'll say a little bit more, obviously, as you move along. Okay, right. There's something else we need to sort of mention here in the next question. So we move to generators now and motors. And as I said, I'm here to give you a very detailed discussion on generators and motors, to look at actually a theoretical lesson that inculcates the underlying theory, that underpins the underlying theory. A simplified diagram of an AC generator connected to a 25 ohm resistor is shown below. The coil rotates anti-clockwise. Okay, you have this coil and it rotates anti-clockwise there. Okay, that is clear there. Okay, and you have that setup. Name the component that distinguishes this generator from a direct current generator. Right. We have seen earlier that this one here is an AC generator. Earlier, we saw a DC generator. Okay, so what does an AC generator have? Okay, an AC generator has these things here and those components. we have a special name. Okay, name the component. So the component is called the slip rings. Okay, so in other words, it has slip rings. Okay, there. And these slip rings are the rings that are present in an AC generator versus commutators in the DC there, or what you call the split rings. Okay. Now, you make the following observation in 9.2. In which direction will the induced current flow in section XY of the coil? Choose X to Y or Y to X. Okay, in section XY of the coil, then I'm here to give you the details, but you need to understand that this one is like a negative terminal of the negative bar magnet, and this is sort of a positive bar magnet, and obviously we expect the magnetic field to move from positive to negative, so you will have the magnetic field that way. I'm here to look at Fleming's left-hand, right-hand motor rule, and or the right-hand dynamo rule. And now, if they ask in which direction will the induced current flow in section XY of the coil, right? So obviously, at this point, because this rotation itself is anti-clockwise, as shown, so we really can see that it will be from Y to X. Okay, it will be from Y to X there. All right, because it is anti-clockwise in rotation, directional rotation of the coil, and now it would be obviously from Y to X. Okay, I'm here to give lots of details on these there. Okay, and obviously the right-hand motor rule. If you look at the next question that looks at the graph below, shows the output voltage of the generator for one cycle of rotation. Okay, we looked at DC earlier, at a red current generator earlier on today afternoon. And now the graph below shows the output voltage of the generator for one cycle of rotation of the coil, like that 9.2. Okay, so this graph is different from the other one because it is for an AC generator, so it comes to the bottom. The other one, we saw that it was just that way there. Okay, and these two were the same, could reach the same potential difference there. All right. Define the term RMS potential difference. Okay, let's define these. What does RMS potential difference? So in 9.3, goodness me, the DC potential difference which dissipates the same amount now the DC potential difference which dissipates the same amount of energy as an equivalent AC potential difference. The DC potential difference, which dissipates the same energy or the same amount of energy as an equivalent AC potential difference. That becomes what we call the RMS potential difference, okay? So what does RMS potential difference mean? It means the potential difference, or RMS potential difference refers to the DC potential difference which dissipates the same amount of energy as an equivalent AC potential difference. 9.4, calculate the RMS current in the circuit. Let's calculate the RMS current in the circuit. So we're gonna look at that one in 9.4. So VRMS. VRMS, the formula for VRMS is gonna be Vmax divided by the square root of 2. Okay, this is how we calculate RMS versus max values. All right, so what is Vmax? We know very well that Vmax is 100. That's what reaches there. So we have 100. We divide by the square root of 2. That's the formula for VRMS. So in therefore, this one here, what does it give us? It gives us 70.71 volts, which is VRMS. IRMS is VRMS divided by R, which is 70.71 divided by R, which is 25. Okay, because now we know very well that at this point, this is connected to this simplified AC generator is connected to a 25 ohm resistor. Okay, so the resistance in there is 25 ohms. Okay, so you'd have that IRMS is VRMS. So I equals V over R. This is Ohm's law. Ohm's law can be seen from the triangle from grade 10. R equals V over I. So I is equal to V over R. So Ohm's law, but if you have IRMS, it must be equal to VRMS over R. What is VRMS? So VRMS is what you got here, which is 70.71. Divided by the resistance in this one, in the resistor there, which is only 25 ohms, and you divide these two guys. And if you do, it's 2.83 amperes. All right, so that is sort of the answer. There, 2.83 amperes. Right, so we have calculated the RMS current in the circuit. Then we need to find now something called the power, the average power dissipated in the 25, in the 25 ohm resistors. So right, so we would find that one 9.5. So 9.5 will calculate the average power. And so this average power, by average power, we mean P average. P average is V squared RMS, V squared RMS divided by R, which is V squared RMS, which is 70.71 squared divided by R, which is 25. So we divide this one, which is exactly 200.00 watts. So which is the average power. So now at this point, we are finding the average power, and the average power is exactly 200.00 watts. All right, so that's what we get. That's what we get there. And therefore, this is the average power, which is exactly 200 watts. We can just write like that. You can just write 200. You can just write like that. You can just write 200 watts. Okay, that's the average power dissipated in the 24 25 ohm resistor. So the average power formula is P average, which is V squared RMS over R. Okay, right, and you can use another approach to calculate this 9.5. So 9.5 you can also use to find the average power. You can also use IRMS, because we know that IRMS is going to be equal to I max. It's going to be IRMS, it's maximum current divided by the square root of 2. This is how we calculate that one. So we say IRMS, which is, what is I? RMS. Okay, so we know very well that IRMS can be determined here in the question. Right, so IRMS in particular, IRMS. Okay, we know that one the question here. Right, so what is IRMS? IRMS. Okay, here it is. Right, so IRMS, we found it to be 2.83, so we put here 2.83 amperes, which is I max divided by the square root of 2. And then we just need to find the maximum current, I max. So I max is 4 amperes. Average. V max, I max. So you can also use this one. That you, if you want to find the average power, you can use average power is V max, I max divided by 2. Okay. Like that. And so what is V max? We've seen is 100. V max we've seen is 100 on the graph. So V max is 100, and then you put the I max. We've already seen I max is 4. You divide everything by 2. You divide 100 by 4 is 400 divided by 2 is 200. Is 200 watts. P average. That is the average power. Now we continue. Okay, 9.6, now we need to copy. Okay, the speed of rotation of the coil in the generator is now doubled. The speed of rotation in the generator is now doubled. So it rotates more and more. So it was rotating, but now the speed is doubled. Speed of rotation is doubled. So now this rotation is happening, but now it's happening faster. Okay. Copy this set of axes below in your answer book and sketch the graph of output voltage versus time for 0.1 seconds. Okay, let's sketch this one. Right, so you realize that the potential difference will increase. It will increase upwards. Right, so the potential difference is going to increase, and then it's going to decrease. It's going to increase, and then it's going to decrease again. And then it's going to increase, and it's going to decrease again. Okay, so the potential difference will go down here, Okay, so we are obviously dealing with AC, an AC generator. Alternating current generator, it goes below. Okay. Unlike the other one we saw, which is AC earlier. So now this would be the dashed lines there, like that. Okay. So now you realize, therefore, that you remember what is being said. The speed of rotation is now doubled. I need to copy and complete these there. Okay. Right. So if the speed is doubled, you'd have obviously that, because you remember a couple of things. So let me see what else to mention. Remember that it was here at 0.05. So if suddenly the speed is doubled, so you can see that therefore it will obviously be now there. Okay, it will be now there at fraction half of that, because this is now faster, and therefore the potential difference is actually obviously more generated. And now if it's more generated, so it's going to be double. It's going to be double that, so it's going to be at 200. Even here is going to be at minus 200. Okay, so also there it goes higher and so on. All right, that kind of thing. So you're going to have that. Okay, right. So that would obviously become the answer to that question. To say, copy the set of x's below in your answer book and sketch the graph of the of output voltage versus time was 0.01. We've explained that. Okay, let's look at what happens in the next question when we are to have some analysis of some of these things. Obviously, some of these things we're going to discuss, we're done at grade 11, but we're just revising them right now. In question 10, we're saying the relationship between frequency F and maximum kinetic energy of photoelectrons emitted from two cathodes, M and N, of different photoelectric cells is investigated. All right, so the graphs below have been obtained from the results. Okay, we have the graphs that have been obtained from the results. And those are the graphs. Define the term threshold frequency in 10.1. The minimum energy. The minimum frequency, excuse me. What is threshold frequency? It refers to the minimum frequency of light needed to eject electrons from a metal. From a metal, or you can say from a surface. The minimum frequency of light needed to eject electrons from a metal or surface. The minimum frequency of light needed to eject electrons from a metal or from a surface. This minimum frequency of light needed to eject electrons from a metal or from a surface, this minimum frequency is called what? It's called threshold frequency. Threshold frequency. All right, let's look at 10.2. How does the maximum kinetic energy of the photoelectrons emitted from cathode N compared to the maximum kinetic energy of those emitted from cathode M when light of a frequency greater than 10.40 times 10 to the 14th power is shown on each of the cathodes? Choose from greater than, smaller than, or equal to. Okay. I want us to look at these very carefully. Again, I read through the question. How does the maximum kinetic energy of photoelectrons emitted from cathode N compare to the maximum kinetic energy of those emitted from cathode M when light of a frequency greater than 10,40 times 10 to the 14th power Hertz is shown on each of the cathodes? Okay, so obviously, as a matter of fact, the maximum kinetic energy of photoelectrons emitted from cathode N, okay, this maximum kinetic energy from cathode N compared to the maximum kinetic energy of those emitted from cathode M will be greater than, It will certainly be greater than. Okay. Those obviously the maximum kinetic energy in actually of the photoelectrons emitted from cathode N will essentially have a greater kinetic energy there. Okay, and obviously that is witnessed by the frequencies obviously there. Okay, so you have the frequencies of 5,16 and the frequency of 10,40. All right, and so the maximum kinetic energy of the photoelectrons emitted from cathode N compared to the maximum kinetic energy of those emitted from cathode M when the light of a frequency greater than these is shown on each of the cathodes. All right. So obviously you can see that for cathode N, the frequency graph is below versus the E max kinetic energy. Okay, and therefore as a consequence, because it is certainly below, right, so you can see that it will ultimately be greater for cathode N than M. Okay, observe that, and I'm going to give more details on the relationship between the maximum kinetic energy and the frequencies involved there. Okay, but I want to mention 10.3, calculate the value of the frequency fx indicated on the graph. We need to find the value there. What is fx? Okay, so fx can be obtained, and let's calculate it. Right, so we're gonna see that E is equal to W naught plus EK max, which means fx is equal to 1 divided by 6,63 times 10 to the minus 34. Into 23. Into 23. Okay. So you'd have that this one here is HF naught. This this W naught. So this
plus 23, 01x 10 to 19.
Okay, so
Fx
okay, so you have 51. That. All right. So you have 1 divided by 6,63 times 10 to the 34th. All right, and then you have the W naught, which would be exactly that one there. Okay. Which would be 23 0.01 times 10 to the minus 19. Okay, you can see that obviously appearing there is the EK max. Plus the 10,40, this one, by 10 to the 14. By 10 to the 14, obviously associated with exactly this value by 10 to the 14. And then we have that fx. If you use a calculator, you add everything here, you'd get 4.51 times 10 to the 15th hertz. This can also be written as fx is 45.1 times 10 to the 14 hertz, which is exactly the value that is wanted there. Okay, I'm yet to look at these in greater detail. Right, so the next thing I'm going to discuss is the 10.4 parts of the exam question. So we calculated the fx there. All right, at this point, we're saying the experiment is now repeated for cathode M using light of frequency fx, but of higher intensity. How will each of the following be affected? Choose from increases, decreases, or no effect. 10.4.1, the y-intercept of the graph. Choose from increases, decreases, or no effect. The y-intercept of the graph. The y-intercept of the graph. So once again, the experiment is now repeated for cathode M. Okay, so we are focusing on cathode M, not N. Using light of frequency fx. So this light is of the frequency fx, but of higher intensity. How will each of the following now be affected? The y-intercept of the graph. For cathode M, how will the y-intercept of this graph, this is the y-intercept, how will the y-intercept be affected? So obviously the y-intercept for cathode M will not be affected. So it will have no effect. The fact that the intensity of the light of frequency X, but of higher intensity, in the end, the y-intercept of the graph will not be affected. Okay, in 10.4.2, the number of photoelectrons emitted per unit time. The number of photoelectrons emitted per unit time. All right, so the number of photoelectrons emitted per unit time. Okay, because the intensity is now higher intensity, you'd have more electrons emitted, you'll have a greater number. So if you increase the intensity of the light, yes, the light of higher frequency, now the intensity of the light is higher, so the number of photoelectrons increases. The maximum kinetic energy of the emitted photoelectrons, right? So what happens to the maximum kinetic energy of the emitted photoelectrons? Well, it is the same light, the intensity is just increased. Okay, so the maximum kinetic energy will not change, so there's no effect. The same type of light, but it is now, it has its intensity having been increased or slightly higher. All right, so we have that.
So can you please re-explain 10.2? I mean 10.4.2.
Oh, 10.4.2. Okay. Yeah, the number of photoelectrons emitted per unit time. I was saying that at this point, because the light, it's light of frequency of X, but it has higher intensity. Because the intensity is higher, the number of the photoelectrons emitted per unit time will therefore obviously increase. Why? Because the intensity is higher. If the intensity is higher, what does the intensity higher mean? So it actually means that you have more photoelectrons emitted per unit time. Okay, so but most importantly, remember that if the intensity of the light is then higher, it means that there are more photoelectrons because the light is more intense, and intensity means more photoelectrons per unit time. If it was dimmer, so obviously you'd expect that it is potentially brighter, etc., than the previous version of the light because of the high intensity. But now, if you increase the intensity, it means more photoelectrons are emitted per unit time. Okay, and that's what light of greater intensity means relative to a light of lesser intensity. If the intensity is less, then it means you have less photoelectrons emitted there. Okay. Obviously, I'm yet to look at possibly a lot of specific examples and illustrations of that so that these can make more sense. But obviously, we're speaking about light from the light source. And the light source, whatever the source of the light is, you are really saying that if you increase the intensity of the light, then you'd have more photoelectrons. What are the photoelectrons? These are the light. Well, the word photo means light. So these are the light electrons. So if the light is brighter, then you have more light electrons or photoelectrons. Okay, so those are the kinds of things we're going to discuss. But it is my plan to look at these a little bit in more detail, and I'm going to look at more sections that relate to this, but also I'm going to be looking at more sections that relate to electrostatics as well. Electrostatics and aspects of something called Coulomb's law. All right, now the approximate time is, I'm going to spend a bit more time on this tomorrow. The approximate time is 21:25, obviously in the evening, right? So I'm sure that the average time is about 1 hour that I planned to spend. But as said, it is my plan to have a bit more theoretical discussion on the theory that we use to answer these questions and how we observe the increases, decreases, remains the same, no effect, as we discuss these questions. And so that is what I'm planning to discuss then tomorrow. I'll send you my thing, my
Yeah.
load shedding. Yes, please.
Tomorrow, can you please have our classes like much earlier? At like
yeah,
3.
that's fine. Yeah, you'll suggest to me, for example, I'm looking at my thing now. I'm looking at my my load shedding schedule, just to see how it at the time at which it's going to happen tomorrow, the load shedding. I'm just looking at it now so that I can have an idea. Right, for my area. For example, I'm gonna have load shedding tomorrow 2 times. So it's in particular, it's gonna be from 6 to 8 p.m. 6 to 8:30 p.m. Okay, and then it's gonna be, well, this is gonna be from 2 to 4 a.m. in the night, just after midnight. So this one is out, but now it's just gonna be from 6 to 8 p.m. tomorrow in the evening, from 6 to 8. So you let me know what I'm giving you the freedom to decide on the time. Yeah, because I'm planning to have a bit more of a teaching lesson on how you need to understand these concepts theoretically for you to be able to define and answer exam questions. So you let me know then what time is going to suit you. Yeah, my load shedding is going to be between 6 and 8:30.
So,
Between
sir,
6
can we have 3 to 5?
Yeah, 3 to 5 is perfect with me.
Yeah, tomorrow 3 to 5.
Okay, yeah, 3 to 5, yeah, is perfect with me. All right. Right, so I'll see you tomorrow at 3 to 5. I'm planning to look at this science in more detail, but a bit more theoretical, a theoretical perspective that will allow you to understand a bit more the concepts themselves and how we arrive at the answers in some detail. Okay. Yeah, but thanks a lot then for joining us today. I'll see you again tomorrow between 3 and 5. Okay.
Okay, and then so tomorrow, can you
ma'am.
like teach
Yeah.
the electricity, not like past papers, but like teach it like
Yeah, definitely. So yeah, that's what I'm actually planning to do. That at least if we spend time on the theoretical aspects, as said, like a teaching approach in terms
Yes.
of the basics to say what really constitutes the basics, the theory, and then so that you can be able to answer the exam questions. Okay.
Okay, thank you, sir.
Yeah, thanks, Karabo. I'll see you then tomorrow between 3 and 5. 3 and 5, yes. Okay, thanks
Bye,
then.
sir.
Have a good evening. Thanks, Karabo. Goodbye.